Any questions? Seems like the last thing we did was we were looking at F equals MA. And then we went into the lab. All right. All right, so I have a mass here. They claim it's a kilogram. Push it. Try that one again. It's a half kilogram, so they claim. I push on it. It left my hand at some point, and then it stopped. Why did it stop? Sorry, I didn't hear.
Why did the thing stop?
Yeah, why did that mass stop? The second one, not the one that rolled off the table.
Because of friction.
Okay. And this is the huge departure from, I guess, the belief in physics, physical science, whatever you want to call it, from BCE era up until 1600s. The idea before was that things had a natural place and it stopped because it wanted to be stopped. And then Newton, standing on the shoulders of giants, as he claimed, encapsulated this idea that objects will do whatever it's doing right now unless something forces it otherwise. So once I started it moving, it was going to keep moving at a constant velocity until something caused it to change. This is known as the idea of inertia. And sort of encapsulated mathematically in Newton's second law, the fact that the total force is equal to mass times acceleration. Velocity is constant unless there's a force applied, and a net force applied. So this idea of friction, so if it stops, there has to be something causing it, and so friction is the idea that we came up with. So let's take a look at friction. So it was moving to the right at some velocity. We did the force diagram. What are the forces acting on the mass there when it was sliding?
Friction.
Going which way on it?
Opposite of the force.
Opposite of what?
The force.
You said the force? What force? Are you giving me Jedi powers that I somehow?
Opposite of.
Does someone want to help Caleb out, or just let him sort of flounder for a bit?
Opposite of velocity.
Or more generally, direction of motion. Yes, opposite of the velocity. So friction's acting back this way. All right, the two other forces acting on it.
The weight.
And from the pencil, you're saying down.
A normal force.
Yes. All right, so we have these three forces acting on it. The weight and the normal force will balance each other out, leaving us with only a net force of the friction right here backwards. So this had friction acting on it. It looks probably work better than this. Wider surface, less likely to roll. So similar to if I push the book, friction causes it to stop, and a little bit of normal force there because it ran into something. There we go. Now suppose I now put something on top of it. It took more effort for me to get it going. It stopped sooner after I let go. What forces are acting on it now? Or, change that, what changed?
There's more weight.
As in the book weighs more?
Well, there's more weight on the book.
Okay, but weight is between, I understand what you're saying.
Okay.
We'll just see, we'll get down to the specifics here. But weight is between the object and the ground.
Is the friction between the weights in the book the opposite from the book to the ground to the table?
All right, well, let's take a look at that. All right, so we've got, I guess we'll simplify it into a bunch of masses on book. So if we did our force diagram here, so I got friction still acting back on the book, I have weight acting down, I got normal force acting up, and then I've got this stuff on top. All right, so what, on the new force diagram here, what's going on?
You have
more contact force.
I heard someone say, start to say friction and then more contact. A complete sentence, a word I can hear, say it loudly.
Is there friction on the top box going to the right?
So you're saying friction going this way?
Yeah.
These are different frictions then, so let's call this F sub B and F sub, there would be, they went that way, so I didn't touch them. Again, no Jedi powers. So the mass on top moves with the book, but why is the friction acting that way? Or in my drawing there, that way?
Because it wants to go that way.
To throw a little bit more detail into that. No?
Because if there wasn't friction, the mass would slide that way.
Oh, so close to the right wording here. As in, if there were no friction, so if it starts like this, if there's no friction and I push this way, this thing is gonna go like,
Yeah.
gonna fall off the table this way.
No, it's just not gonna move. It's gonna stay there.
So it's moving that way relative to, not the ground,
To the book.
to the book. Yeah, that was the piece that was missing. So if there were no friction there, right way to look at it, it would slide backwards relative to the book, not to the ground or the table. So that's why it imposes that relative motion. All right, so I have friction back that way, so I've got friction back this way. Since I have more than one object, let's throw the subscripts in, all right? And what the heck, let's put the table into it also, or table ground. We'll pretend that the table is part of the ground.
There's normal force from what's on top acting down on the book.
Okay. So we've got this normal force acting down, so Y sub M, Y sub M.
There's weight coming from the top box to the ground.
Let's work on the wording. I'm drawing the arrow on what object in what direction.
The top box down.
Okay. So I got weight of M, weight of, all right. I think that's it. We missing anything? Let's see. Friction, we got 2 points of contact and we got a friction pair there, so no tension, no other, because we're coming into play after it's already moving. Weight's gone, our weight peaked out, and normal force. All right. So, The friction between the book and the table increased when I put the masses on top. These are the forces acting on the book. What changed? Which of these, besides the fact that FB got bigger, what changed here? When I put the masses on top of the book, which of these forces changed?
The weight going downward on the ground.
What's the formula for weight?
Acceleration due to gravity times. Hold on, I know it.
Acceleration due to gravity times mass.
Yeah, mg. Yep, it's good to know. All right, did the mass of the book change?
No,
Did the acceleration due to gravity change?
no,
Did the weight of the book change?
no.
No. All right, so weight of the book does not change.
Contact.
Say it again.
Contact.
Keep going.
The book and the ground,
What do you mean by contact?
like the contact forces.
Okay, the normal force?
Yeah.
Okay, yeah. The normal force changed because suddenly we have this additional force coming down from the top. That, no, this weight right here, sorry, wow, misspoke. This normal force right here in the same direction as the weight of the book, both pressing down, so the normal force here has to increase. So it has to hold up more. What I'm getting towards is that friction depends upon the normal force at the point of contact. So FB depends upon this YB normal force. FM depends upon YM. It's the normal force where that friction is being applied. So in the late 1700s, someone actually came up with a formula. Friction is equal to mu y. Now we're going to amend it slightly, but that's the essence of it. Now, typically in a textbook, they talk about two different kinds of friction. And for those who have seen the videos, what are the two types of friction? Grace, it looks like you're about to come up with an answer.
Is it, I'm trying to remember.
Okay, one deals with movement, and the other one deals with not movement. If that helps.
I don't recall like the term for it.
Okay. Movement. Got the Greek word kine, as in kinematics, kinetics, kinesiology, kinescope, all dealing with movement. So in other words, if they're sliding, you have kinetic friction. Now, because writing out kinetic friction is too many words, too many letters, too much writing, we abbreviate it as by Baroque F for friction, and then with a little subscript K to indicate kinetic. So my formula for kinetic is just that, except I'm going to put some subscripts in. So Fk is equal to mu K times the normal force. Static gets a little bit trickier. As I push on this table, is the table sliding?
No.
All right. So static friction is keeping it in place. Now I'm going to push harder. is it sliding yet? So I'm applying more force to the table, so the friction has to match that. If the friction did not match my force, then it's going to slide one way or the other. So the static friction starts out, there's no static friction because there's no desire for it to slide anywhere. I now press a little bit on it, the static friction matches me, static friction matches me, static friction will match me until I get to a breaking point, and sometimes I can time it right, until I get that breaking point and suddenly it'll start to move. So static friction, let's put that not sliding, static friction. Yes. So static friction is less than or equal to USY. Y being the normal force.
What does the U stand for?
This is a Greek letter mu. And so U sub S is the coefficient of static friction. It is a number. Usually, in most cases, yeah, not every case, almost every case is a number less than 1. Bigger than 0. And U sub K, someone want to tell me what that stands for? Or what that is?
Coefficient of kinetic friction.
Yes.
Is that also gonna be between 0 and 1?
Yes. Now, under this model, US is going to be greater than 0. Well, actually, there are situations, there are frictionless surfaces, but reality, unless you start dealing with superconductivity, you're not going to run into that, where it's equal to 0. And usually less than 1. If you looked up, I've heard rumors of it's being bigger than 1, but I have not seen in any table where it's bigger than 1. And then kinetic the same. And U sub K is less than U sub S. The idea is once you get something moving, it is easier to keep it moving than to get it moving to start with. And under this model, if you think about on the friction is a bunch of, well, you've got a bunch of, there's a surface down there. And if you look up really close, you've got a lot of places that it's not smooth flat. There's some up and down nooks and crannies. And so I've got two objects with nooks and crannies sort of interlocked, kind of like a badly fitting puzzle. If there's a lot of normal force, they're really jammed together. If there's not much normal force, they're not jammed as much. But once you get it moving, we're sort of going across the tops there, and it's much easier to do that than sort of to dislodge it. There's an alternate theory. This is the theory that we're working with, or the model we're working with. There's an alternate model which says there's really no difference between US and UK, that experimentally, when you will find them, the numbers are so close to each other that there's really only one number. Under that model, they say that the friction, whether it's static or kinetic, is less than or equal to this universal mu times the normal force. Now what that would look like in a graph, because everyone loves a graph. If we had plotted friction versus the applied force. So applied force, I'm pushing on a table, eventually it'll start going. Under this model, with the US and the UK, the applied force is the friction is gonna match the applied force up to a breaking point, at which point the friction drops down into kinetic. So this is the kinetic friction. This is the static maximum static friction. Max.
So it's like the cause of friction just because like the ground and everything like that is like imperfect and it's not like.
Yes, maybe. Sorry, I know that's vague. I think that is a perfectly adequate way of looking at it, and I have not run into a situation where looking at it that way would fail you. In the alternate model though, it's actually, instead of being this resistance and you got a bunch of tiny little normal forces that we're calling friction, that is actually an attractive force, that you got the atoms really close to each other from one surface to another, that they're attracted. And then the more nooks and crannies means the more surface area that will be touching and more attraction. Under that model, so under this model, friction versus the applied force, friction is going to increase and then you hit a breaking point and then it just levels off. And so this is the kinetic friction, which is also the maximum static. Two different graphs. You would think it'd be easy to test this. I tried to find someone who actually tested this, and I found one paper where they tested this, and the error bars were so large you really couldn't tell a difference. Not enough to distinguish US and UK, although US was slightly larger than UK, but you know, it's like the values from US he was getting would be in this range right here, and from UK they were this range. So there was some overlap. The reason why it really hasn't been figured out, this is my opinion of it, is that physicists typically don't work with friction. That's more of an engineering problem. Engineers, being generally practical people,